I remember that. That's so.
How sick are you? You sad? Oh my goodness, there's a big smile and like clearly a runny nose. Okay. Wrong password. How's Super Bowl?
I didn't watch it. What is the Super
Not
Bowl?
good.
How was Rihanna? I thought she was very good. I don't really think I would describe myself as someone who particularly enjoys her music, though I do know all the songs that she played. She's not a favorite. Yeah, correct me. You can laugh at me. I thought the show was amazing.
The end game. Not
Wait,
good.
what is the Super Bowl?
The halftime.
What is the Super Bowl?
How old are
Oh,
you?
Thomas is on this website.
Thomas
I don't know. I didn't
No,
even know
Tim.
what the world thing was.
Yeah, he's in a
last-
lot of
like,
things.
world.
I mean,
Yeah, I didn't even know what that was. I've lived here my whole life. But
Like the World Cup, you would expect someone who didn't live here to have a higher understanding of.
We're not a sports team. We're a sports family.
Yeah, I see that. So apparently there's a common enough typo for Super Bowl that's superb owl. But the internet fills up with owl pictures on Sunday as well, so maybe you can be on the superb owl team.
Yay.
Trying, girl,
Did you
trying.
watch it?
What, no.
I was, my mother.
I watched it, and then, like, literally, it was like 35,
Did any of
35.
you watch it?
I watched it start through finish.
I just looked at the
Why are
halftime
you
show
doing
for
that?
like 30 seconds.
You don't have
And
to
it
look.
looked really weird, so I just left. And I don't really like Rihanna that much.
Well, no, I didn't, like, I was fine with the halftime. It was the game.
It was people in mosques and hoods, and they were doing like.
Did that make the check-in easier?
Game, like, it really took me.
It was something so.
All I saw was like government stuff. I mean, seconds. And Rihanna's so overplayed. Like,
You know, someone compared Rihanna's halftime show to Super Smash Bros.
Super Smash Bros. Oh yeah, that's what my
You know, like
sister
how
was
it
saying.
happens with like Rihanna's like kind of floating and like
Oh, spirit ranking? That's some nonsense.
Like, looks like a map.
The website is so pretty.
Yeah. They said Marley.
If we get bored, we can do trapezoid rule with Sophia. That seems very doable, everybody. I understand the trapezoid rule. I don't know how to do the test in chapter 14.
I'm gonna come back.
I know how to do the C test because, you know, I got to publicly shame myself by not understanding that, so. Feel free, you know, anytime you want to mention that I think it's showing and you don't. Woo. Enthalpy change.
I do. I need to walk again.
I don't know what other buttons to push, guys. about, it's called energy cycles, and I guess you're right that there's quite a lot of memorization here. You have to know what those representative equations are that allow you to get around the cycle. So right here you can see representative equations like this one. On the multiple choice, you'd have to actually know which one that is. They would say, is this solution or hydration? And you'd be like, I'm not sure. So let me remind you that this is hydration. Then solution is dissolving a solid state compound as opposed to a gaseous ion. But those equations are also going to include hydration, ionization, atomization, electron affinity, lattice, enthalpy, the breaking of covalent bonds, and solution. You want to write them down? You want to see what the notes have? What are you feeling? You want to see what the notes have? Okay, down with that. So we're going to put these together in 2 cycles. One of them is the Born-Haber cycle, and the Born-Haber cycle is going to start with a lattice of an ionic compound at the bottom, and it's going to go around in some big circle. Perhaps you remember some of the states in this circle. I don't really know where you are. But I've thrown in the lattice enthalpy. The reason that we're doing this is because we believe that energy is conserved. And if energy is conserved, if you start here and do whatever you want, but end up here, the sum of all the delta H's will be 0. And so the idea is that I don't have a good way of measuring this particular thing, but I might have experimental techniques to measure all of the other stuff in this like crazy pathway. That's how we're going to do it. You might think that you could do some math, perhaps, to relate how the sodium ions are going to coulombically attract the chloride ions, and think about the nature of the packing. It's a face-centered cubic array. And maybe we could get some sort of an infinite series, and that is called the Madelung energy. And so there is a mathematical solution to this. So maybe it would be a way of finding something over here as well. So this is usually the one we're solving for, but maybe we're going to math this one really hard for our math IA and then compare it to something else. What made your syllabus interesting, and we're all real excited to find out if we have to still know this, is that we also talked about the enthalpy associated with dissolving a salt into water. We refer to this process as solution, and this process as hydration. And so because this was sort of unique to your syllabus, we found that there were a few more questions, honestly, about this little piece of the cycle than there were about this big, harder cycle, which seems kind of like a win to me. But generally speaking, we need to figure out how to construct that Born-Haber cycle, where I've put in 2 of the things. We also need to construct cycles that connect hydration, lattice, and solution. That's what I tried to do in red. We should be able to solve for any of the steps. And we should be able to predict how big the delta H of lattice or the delta H of hydration might be for any sort of periodically relevant set of stuff. So I should be able to go down the table and tell you the charge is constant, the size is bigger, so the coulombic attraction is weaker. Or I should be able to go across the table and say the size is as similar as I can keep it, but the charge is bigger, so the attraction is stronger. Amarachi.
Why does the hydration enthalpy thing have 2 arrows?
It has 2 arrows because I got to hydrate both the sodium and the chloride, and that's 2 different numbers in table. Hopefully we'll figure it out together, Amarachi, in a minute. I don't feel like those lab experiments have anything to do with this chapter, so I'm just going to go on. So, again, there are a lot of characteristic reactions here, and so knowing the definitions of those is probably the hardest part, why this is a memory chapter more than a skills chapter for some of you. And so the enthalpy of formation, we're going to read this as standard enthalpy of formation, is always defined as taking elements in their standard states and bringing them together to make what it is we're interested in. So here we have the metal sodium. We're reacting it with chlorine gas. Chlorine is, of course, diatomic. I'm always going to make exactly 1 mole of my product. And so I've got to put that half in there. That makes some of you feel gross. But that is the enthalpy of formation of NaCl. And so if I were to write it here, I would show you sodium solid and chlorine diatomic gas coming together to make NaCl. Now the direction of my arrows is meaningful. This is like the yields arrow. So I'm describing to you what the reactants are and what the products are. If Brecken wanted to break apart sodium chloride into its component elements, he would have to take this delta H and negate it. So it is exothermic to mix the elements together to make a salt. It would be endothermic to take the salt and put them back into elements. Since we're trying to complete this cycle, you can imagine that we're going to have to take these elements and we're going to have to make sure that they have a charge, that we're going to have to turn them into atoms. And to turn them into atoms, we use something called atomization as like a generic word that describes taking sodium the solid and turning it into sodium the gas. This is going to be endothermic because we know about phase changes, that taking a solid and putting it into the gas, we have to break those metallic bond interactions. So this would be the delta H of atomization of sodium. This would be the delta H of formation of NaCl. And give me a number, we'll figure it out. We actually have 2 choices for how we handle the chlorine. Them? That's right. So we can talk about the energy required to make a chlorine-chlorine molecule into 2 chlorine atoms in the gas phase. And that's known as the bond dissociation enthalpy, and that's what we find in table 11. So this could be 1/2 of the bond dissociation enthalpy of the chlorine-chlorine bond. Or it could be written as the delta H of atomization of chlorine. Those 2 things should have the same value. It just depends what they give you in the paper. So now we have taken our NaCl solid, we separated it into the 2 elements. We took those elements and we atomized them into sodium atoms and chlorine atoms. What's the next step going to be? So we're going to have to add an electron or remove an electron. This is an example of removing the electron. We're going to use the ionization energy. It's the minimum energy required to remove an electron from a ground state gas phase atom. And I'm going to remove that electron from sodium. So I'm going to make Na plus an electron, and this is the ionization energy of sodium. This is in table 8 of your data booklet. So part of this was like a really strange scavenger hunt that I'm sure all of you really enjoy. Remembering where it is you can find this in a booklet. And as Audrey said, the other step is going to be putting an electron onto the chlorine. That step is actually exothermic, and it's known as electron affinity. The electron that we're putting on is that electron right there. So that electron and this chlorine are going to come together to make a Cl- gas. That's also in table 8. I'm going to try and make this look better. Because I messed up and I want you guys to tell me what I did wrong. I didn't mess up bad, just messed up. So what I had done was just tell you what I was changing. So I said to atomize sodium, I'm going to take sodium solid into sodium gas. What I'm admitting this time is just that the chlorine is still there. Okay, I just had ignored it. Same thing here. I'm going to atomize the chlorine, so there was my chlorine that I made, but the sodium gas is still there. I'm gonna ionize the sodium, but the chlorine gas is still there. I'm gonna give this electron to the chlorine, so I've made my product. Do you notice that's exactly what I was hoping to make? I just felt like there was gonna be one more step because it's been a minute. I'm just gonna, woo, that arrow, because there are no more steps. Yes, I hear the erasing. Again, like there's nothing grievously wrong, we just had two levels that were the same energy. The enthalpy of the atomization is not in the data booklet for the metal, but it could be in the data booklet in table 11 for the non-metal. So the one for the metal has to be given to you, but if we're breaking bonds, you can handle it for the non-metal. Again, it's just a scavenger hunt. Miserable scavenger hunt. The last one we have is the lattice enthalpy. The lattice enthalpy describes taking a lattice and blowing it apart into the cations. They gave me that number, 771. It is always going to be endothermic. It's unclear what we're solving for here, but one of the difficulties that you may have experienced or may not have is that the arrows are vectors and they don't always match up with exactly what you want to do. So if I had been trying to solve for the delta H of the lattice, that is, if I was trying to get from here to here, I would tell myself that there's another pathway that's to go all the way around. But the first thing I might come across is the fact that this arrow is pointing in the opposite direction, so I need to flip it. So the arrows are directional. And that's that.
It's 771.
Thanks. Do you think we can solve for the atomization of sodium? Yeah? Let's see. So I'm going to try to get this one. And I believe that Yash, who's not in this room to defend himself, was of the opinion that the easiest thing was just to memorize a formula here. And so he just wrote down a formula for this test. And he knew it, and he got it right, and go Yash. But Audrey agrees with me that that seems really hard to me. It seems easier to think about this as a picture, not necessarily as a sum of equations, but as a picture. And so then maybe I have a shot at saying, if this is what I'm solving for, it should be equal to, so I'm trying to get from here to here. So what I'm going to do instead is I'm going to start here, and I'm going to go around the circle that way. Does that make sense to everyone? So I'm trying to get from this point to this point. This is the value we think isn't in our data booklet. And to get from this point to this point, instead of taking the direct path, I'm going to start here, and I'm going to go through all of these other things to get to that end point. So now I've got to think about the signs on stuff, and I chose this to be awful, right? I don't know that you guys would have solved it this way. I'm just trying to prove a point, poorly perhaps. So I want to go from here to here in the direction of this value, so I'm going to write down minus 411. I want to go from here to here in the direction of this arrow, and Moheb told me that I don't read well, so I fixed it. We good? I want to go from here to here, but I want to go against the direction of this. So I'm going to look in table 8 for the electron affinity of chlorine. Are you screaming it out? And I'm just too dumb. Minus 349? Thank you. But I'm going to negative that. Why am I going to negative it? I'm going the other way. Next thing I need to do is ionize sodium, blissfully on the same page, but I need to negative it, so I'm going to write down minus 496. The next thing I need to do is this step. It's the last thing I need to do, so I'm going to table, oh, you're going to tell me it's table 11, aren't you? Table 11 is going to tell me that a chlorine-chlorine bond is 242 kilojoules per mole. I'm going to take that number, I'm going to divide it by 2, because I only want 1 mole of chlorine, so this would produce 2 moles of chlorine, and it describes breaking a whole mole of chlorine molecules. And so I'm going to subtract 121, and that should be the atomization energy of sodium. So 242 is the amount of energy it takes to take a mole of chlorine molecules and turn it into 2 moles of Cls. I only want to make 1 mole of Cls, so I took that number and divided it by 2. Am I expecting a positive or negative number?
Positive.
I got 92. Did you get 92?
Yeah.
Questions on that? Yes?
So just to recap, it's from NaCl solid, it's the enthalpy formation, then it's the atomization of sodium, then the atomization of chlorine, then the ionization energy of sodium, and then of chlorine, no, EA of chlorine, or
Yes, EA. Because we're giving an electron to it, it's an EA. Here, see. I don't know that I love this picture more.
So you give ionization energy of sodium, and then EA of chlorine, and then
Lattice enthalpy.
what about that one, the one that goes down from EA?
So this is 1.
Or
So we
like
took
that?
chlorine and we gave it an electron. This is the EA of chlorine.
So that would be the EA.
That whole thing is EA. I just drew it poorly, and so I tried to fix it.
And then from there back down is lattice.
Yes.
Do we have
Except
to-
lattice enthalpy goes up.
Oh, true, because it's solids, gases.
Do we have to know the definitions of each like lattice stuff? Or like each entity stuff? Like formation?
I would say that the definition of ionization energy and electron affinity would come up in a chapter 3, a topic 3 question as a legal definition to give.
Like the stuff that it says like it's like 1 mole of this to turn it from like a solid to like a gas or like those kind
I
of
don't suspect that those questions would come up, but I think that the mistakes that are made are not recognizing that 1 has to be the coefficient of the product in all of these. So as long as you're on that, I think you'll be good. Amarachi?
Is center enthalpy of formation, is it going down?
Yes, because we're taking elements and turning them into what we want, the salt. So enthalpy of formation, I would say, is on the list of yes. So formation, ionization energy, electron affinity, I would know definitions for. The other, I would just have like a working sort of what is this?
It's not here, it is.
No. It varies. So Anna's question is this number guaranteed to be negative? And I don't believe it is.
Is this presentation off the
I'm working on it. I was gonna try to put one together that had Pearson PowerPoints for all of the chapters. I think they're nice and you've not seen them before, so I think that's good. So if we want to just talk about the magnitude of the lattice enthalpy, I think we already said this, but the 2 things you're looking at is the size of the ions, and the charge of the ions. And so I think that that tracks hopefully with your expectation that the strength of an interaction is a ratio of the charges to the size. Yeah, that's my favorite formula. I know. And so on a multiple choice question, no one would assume that you know the ionization energies of anything, but they might ask you, like, does this make sense? And so going down the table, you can see that the numbers are getting smaller, and that's because we have a larger cation with the same anion. Going across the table, it's a little bit confusing because this is the middleist in size, so that you really wish that say it said. This is the largest, the middlest, and the smallest. This one here is more charged, but of similar size, so you can see that's a pretty big factor. When we double the charge, our naive approach would be to double this value. Same thing here. If we were to compare sodium and magnesium, we might expect that when we double the charge, we double the value. It's not a great answer, but at least it's an expectation. If we compared magnesium and calcium, we probably would have expected them to be more different. But you know, that's where we are. I can't fix numbers not being perfect. MgO is going to have a +2 and a -2. So we'd expect it to be about 4 times bigger than NaCl with a +1 and a -1. If we had to compare it, it's ballparky. Oh, they're gonna draw it for you, okay. I'm gonna click through these because I think I did them on that board, but it's gonna, it looks like it's gonna be scaled and stuff. Let's see how it looks. So we started with the 0 of energy being 2 elements in their standard state. And the first thing we did was atomize the sodium. So you can see the red sodium atoms were in a nice metallic lattice and they are separating. Everyone feel the picture? Oh look, now chlorine is being atomized. You have that molecule and we're breaking a covalent bond. And so I don't love what this says. I think this should say 1/2 of the bond association enthalpy. It's not 1/2 of the atomization enthalpy. Right to the publisher. The value we talked about. And we're going to ionize the sodium. That is definitely a big cost of this reaction. What would it look like if I had magnesium 2? It's going to look bigger because not only do I have to do a first ionization energy, I have to do a second ionization energy. What else is magnesium going to change here if I had magnesium chloride? I'm going to have to do the chlorines twice. So I'm going to have a whole chlorine, I'm going to have a whole chlorine, but this I'm going to have to do it 2 times, so it would be twice as much. Okay. If we had MgCl2, I'm saying you have to prepare 2 moles of chlorine atoms now instead of just 1.
So you wouldn't have it?
That's right, you would not have it.
That because Mg has a +2.
Yes. So Quinn's first thought was that we were going to have to ionize it a second time because magnesium has to be not +1 but +2. But another thing we're going to have to do is we're going to have to take a full mole of chlorines and make 2 moles of chlorine atoms. And so we wouldn't put that half in there. Now we're going to give the electron we just stole to chlorine. Oh my God, a lot happened there. And then we're going to take the positive and the negatives and we're going to bring them together to make this lattice, which is the lowest energy thing on there. This is the -411 that you wrote. So that is our cycle that we wrote, ugly on the board, all pretty. Sometimes they'll ask you why a value that you got isn't consistent with what you might expect. And the official answer is because of the covalent character in the compound. So typically what you'll find is a lattice is a little bit stronger than you would imagine it to be. And the reason that it's a little bit stronger is because in addition to that ionic interaction, there's also some covalent bonding. The covalent bonding is going to be better for bigger things. So our wrongness is going to be bigger for larger ions. So 1 mark question, the answer is covalent character of the bond. Barbara's going to make a flashcard. We're all going to be jealous and wish we had our own flashcard. So if you look at the difference between sodium and silver, silver has a much larger discrepancy because it is a larger ion and so has more covalent character in the bonding. So some new definitions for your syllabus for solvation. That's when we take a gas phase atom and we put it into water. All of these are exothermic. Why do you think aluminum is so much more exothermic than lithium? Because it has a really big charge. Why do you think sodium is less exothermic than lithium? Bigger size. It is the same arguments that we were making. I was going to talk for 20 minutes, 30 minutes. Sorry. I'm not quite poking my eyes out yet. Look at that. I just have practice problems for this unit. They're doing stereoisomers. I don't remember what you're doing. Yeah. Yeah, they're doing stereoisomers. You both wanted hybridization, so I thought I might keep that for Thursday. I don't remember what your other one was. Okay, I'll send a note. Good? So the new ones that are in 15.1 outside of the Born-Haber cycle are solution. This is taking a solid and putting it into water. To answer what I perceive might be Emma's question, these can be both positive and negative. So if you've ever had one of those instant cool packs, when you mix ammonium chloride with water, it gets cold, it is endothermic. But if you've had an instant heat pack, when you mix sodium hydroxide, that's probably not what they use with water, it gets hot. So there is no known sign to this enthalpy, it does vary. Solution plus something. I can't do that.
Hydration plus solution plus something.
Yeah, there's, I mean, so I would say that the delta H of the lattice is equal to the delta H of the solution minus the delta H's of hydration for the anion and the cation.
Yeah, that was the question.
I don't know, we'll see if I got it right. Hydration, again, this is something that you have to appreciate the difference for. It's a multiple choice question that I'll give you in a minute. Like, they just want you to circle the one that is hydration. So really the point is, do you know the difference between hydration and solution? Hydration refers to a single ion. So hydration is not something that you will ever do. But solution is. You dissolve solids in water all the time. So hydration is like the weird one in my head. It's the one that is not attainable. But it is taking an ion of either charge and putting it in water to form an aqueous solution. This is always exothermic. This is the last slide. I feel like I should walk here. Let me try harder for you. Really not what I was looking for, friends. Okay, that's that. So calculate the enthalpy of solution for sodium hydroxide using your data booklet, and given that the lattice enthalpy for sodium hydroxide is 900. So again, lattice enthalpy is going to be taking a solid and turning it into ions in the gas phase. And we know that this is an endothermic process with a delta H of 900 kilojoules per mole. What we're asked to do do is find the enthalpy of solution of sodium hydroxide. Solution is going to be taking a solid and dissolving it in water. When you dissolve a solid in water, you break the lattice and you separate the ions and allow them all to be encompassed in a sphere of waters. So this is the delta H of solution. This is what we're solving for. And presumably in the data booklet, we can find the delta H's of hydration for sodium and hydroxide. Told you I didn't know the table number. I was not lying to you. 20? And so I get minus 424 for the sodium. And I get minus 519 for the hydroxide. So we've got to, oh, there you go. The delta H of solution is the delta H of lattice plus the delta H of hydration. It's a nicer way with no negative sign. It's the same, I think. And so instead of going directly from here to here, we're going to go around the circle. And so we're going to take 900 minus 424 minus 519. And we're going to get negative 43 kilojoules per mole. And if you remember, approximately a year ago today, you guys are actually measuring this in a coffee cup calorimeter. In a styrofoam cup, y'all were mixing sodium hydroxide with a thermometer, and it was this. Good times. Brecken's the only one who can make the face of what are you talking about. I'm so tired. Miserable. Happy birthday. So this is 33 marks. There should be 45-ish minutes. I was trying to make it so you could finish it in class and we could help each other with it. The way that I have opted to do this, and you can tell me it's right or wrong, is that if I have a problem that has a significant amount of 15.1, I'm giving you the full problem so you can see how things integrate together. So this isn't just 15.1. I don't know. Fridays was fun. We did different things. We'll see if yours is fun. Bigger when the charge gets bigger. When the size gets bigger, it should be weaker. We're going back to the slide. This one? Not that one. This is more than I want to wear, so I'm just going to do that for a second. I don't like the word nucleus in that sentence, but so we're talking about the interaction. Are you latticing it or dissolving it? So the idea is I have a positive charge and he has a negative charge. And if I'm lithium and he's fluorine, I can be here. And we're gonna have a really strong interaction. But if he's iodine and I'm francium, I'm gonna be here. And just the fact that we're so much farther apart makes the interaction weaker. Shells, yes. Is this the one you want? Have I guessed? I don't know. What is the enthalpy solution of that? The lattice enthalpy is that. So I take that positive, and then I'm going to take a minus and a minus. Yes, I get B. I agree with you. I legitimately have not done this. I printed it before class. I managed to do 15.1 with them, so I thought I could manage to do 15.2 with you. Or vice versa. What?
I think it's actually really distracting, because K and RV at work, and VR, or research field and VR, they're going, I just would love to see It's just strange to see the format of this, so we just, for some reason, I was like, oh yeah, NAKRV is just going down and it's increasing, but then they like randomly picked it.
Yes, it's weird.
Oh, that's your bathroom.
I'll go officially get. You get it.
Well, yours is harder. That's what I'm saying.
When you said that, if the arrows are slowly changing and focus on hydration, sodium and applying, how come the sodium was
Because I miswrote.
Oh, sorry.
Don't be sorry. Amarachi caught a righto on the board in case you made the same righto. We're making both things aqueous. What solution is taking a solid and dissolving it in water. What hydration is taking a gas and making it aqueous. I just written a G there. Solution is lattice plus hydration, yes.
Why is there a blank space? Okay, as long as they don't have to.
Does it look better now, Amarachi? Okay, sorry about that.
It's the second one. It's the news and electric. So the first one, you're using the first one.
How's it going?
Oh, no, that's when you. Well, yeah, you lose that, but that's.
Yeah.
That's not that bad.
Does that make the energy like?
That's what I drew.
It's lower compared to the rest because they're like,
Because they're a full shell.
and they're from a higher energy shell.
They're the same
They all have one valence
Yeah, I don't know.
electron.
That's the same number of valence electrons, then I put one, then I thought about putting an S1, and then I wondered what else I could write in that box that might possibly give me more.
It must be some. I guess yeah. No,
It's only one box. So.
because it's like looks like solid sodium.
Maybe. Oh, ionic bonding.
Dr. Hennessy?
Positive sodium.
Oh, ionization. Wait. What are we doing? Do we have to calculate anything? Or do we just...
I think we're trying to find.
Try to write it on the board in a
There
second.
you
We're
go.
trying to find this. Because we'll have 2 minus. Okay. We're trying to find the. For this one, it's gonna be this energy plus that energy plus that energy.
It says use section 8 of the data booklet though.
Yeah, so section 8 of the data booklet, you would use.
But we don't
because
actually...
here it's like
But this is...
ionization.
But we don't actually need to calculate it.
Yeah, we do.
Because what they're asking for is the ionization energy and the electron affinity. But the data booklet has that. So we don't
No,
need
but
to...
here, look, it's going from this step right here.
To me, that's the formula.
It's gonna be this
Oh,
one right
so-
here
Four
plus you're gonna have to add.
I see.
Like, let me just think. And then
Okay, that makes sense.
but then you have to do the same thing with
Needs to be added more.
No, you did that one.
But it's the atom energy.
No, it'd be like the standard one, like,
We'll have a half, yes.
you're trying to find.
Usually we take the half of the
So
chlorine.
you're knowing that it's all to
Yes.
3x the length and x the width.
I think that's why I
and then we need
struggle to memorize it, because it's
ionization
so
energy
not
for oxygen.
perfect every time you have to think about it. But like, again, Josh got it right, so I can't say it's not the right thing to do.
Is that only for
Sure, you can look at
the X?
So X is meant just to be whatever the non-metal is. So for the non-metal, I have to atomize it, like you said, we do that by breaking bonds, and so sometimes we need the half there. And I have to give it an electron, but maybe 2. And so that's the electron affinity of X. And then the metal is M, I have to
So like small,
It's like, so you want the smallest radii.
small size high charge.
High charge, yeah. So the charge for the oxygen is 2 minus. The charge for the sulfur is also. I also crossed out B in papers. Sodium has a smaller radius. So then I was just like, oxygen for the oxygen also kind of has a smaller radius.
Well, I don't know if it's going to be an iron charge.
Yep, they have the same charge.
Oxygen is also.
2 minus.
Oh, it's not. It's true. So it's just again small size of A.
Yeah, that's what I did. I don't know if I'm right.
Is he like it? Is it better than like
I would say no here, because they've asked you not to go to the one. But I would say yes here, where they're asking for you to do. Yeah, the two values are both in the table, so you have the negative and then you have the really only do that for these two. Yes, you have them together without changing any signs. You have them together.
Did you?
So for this right here, because 2 ionization molecules.
Wait, there's two. Oh yeah.
So 107.36, that should be 603. And then for this one, it should be negative 12.
For D, I got 861 and 603. 02, they told me what it was and atomized it, and then I took the minus 141 and the 753 that are both in the second ionization energy. Over there is second. Oh, second.
I didn't
Just
know
gotta go back
that.
over
Okay,
here.
As long as we did the same.
No, you have to add 49. So it's going from
You would have seen it when I did it.
Oh yeah, that's what I did.
Oh yeah.
Yeah.
This one is right.
249 and negative 141 and 7. This is actually pretty easy. Last year I was struggling so much.
Oh, so that's like the. That's this right here.
Yes, the big
Oh no. It could be a point. So it's no. It's positive. Because going this way, should be positive. Lattice associated positive. Positive. Should be like that.
Do we have to multiply anything by 2? Oh, formation.
Of course, right here. This is wrong. So we would do.
multiply the wrong thing by 2. Wait, no. Why would you multiply by 2? Wait, actually,
Two
you should
is
multiply by 2.
two is getting atomized. 2 is getting ionized. I only multiply. Oh wait, I think I only did.
Are you supposed to multiply both by 2? Is that
Wait.
right?
I think I did one. I missed one thing.
Maybe they both need to be.
So then you need 2 and 8 because Na has 1.
Yeah, 2 and split by 2. I think you need. Did you multiply both by 2?
I did too. I know it should be positive.
I think you needed to multiply more by 2.
Why more?
No, more by 2.
Which one? Like which one out? What the other? should I
Everything with
multiply
the everything with the sodium.
by? I did do everything with the sodium.
Oh, you multiplied all that by 2 and you still got the wrong answer.
I did everything. I multiplied. Okay. I
Wait, what did you
multiplied-
get? This.
Yeah, we're both wrong. I multiplied this by 2, right? Because 2 sodiums are getting mixed, right? Nothing happens to the sodium here. Just the opposite.
Yeah.
But I kept 249, even though I don't know if that's. Now here, 2 sodiums are getting ionized. 1, 2 times the ionization.
Yeah.
Then nothing's happening to the sodium here. It's just this.
Did you also have turns? But what if they gave us random values? What was the right answer? Yeah, the internet might do it. So maybe we were right. Did you get the same answer?
I got.
Do you get 280?
Representative compounds.
Oh, that's right.
That's not what's wrong with it in that story. That is not what's wrong with it. It assumes something about all the compounds. It assumes that
Oh,
they're
but
all.
it's done at
I got
standard.
2481.
Or standard pressure.
Okay, but it
For
assumes something else.
wait, where did you?
It assumes that everything is
What
in the
did you
gas
do differently?
phase. And so we know that we have
I go
solids, so we know it's.
889.
Yes.
Why did you 2 times 1?
2 times because.
Or no, I did 2 times 1.
Yeah. Yeah.
Why did you 2 times 4?